Swayam Prabha. Digital India. Educated India.
So last class I was telling you about LCA life cycle assessment or life cycle analysis framework. So there are standards, ISO standards by which this has to be done. So if you recollect, there are 4 steps. Okay, so first we have to define what are the scope and purpose of the of doing LCA. That pretty much saying that why do we want to do LCA. The second thing is about inventories, database. All the material, energy, process related matters, process related quantities, we need a database, okay, that goes as an input. And the third thing is the impact analysis. You basically calculate how much energy required, how much emissions, greenhouse emissions, how much waste is created, how much land pollution, air pollution created, and then also doing the interpretation, what it means to calculating LCA and what do we do with this data, right? That's the analysis part. So as I said, now every business tries to do LCA for their products. Okay, if they want to produce a EV vehicle, they do an LCA. If they try to make any other product, there is always an LCA component associated with it. Now, I want to focus a little bit on today on plastic resins. Okay. So as you recollect, in the plant visit that we did, they basically get this nylon resin imported. So somebody in the US, DuPont and various other companies make resins of nylon 6, nylon 66 and other variants. So now and there are many other kinds of resins, not only nylon. Okay, so there was a study about what are the LCA of these plastic resins. Okay, so in this particular class I will talk about a couple of examples and also to compare the relative impact, and then also talk about bio based PLA LCA also. Okay, so here we are talking about only plastic resins, not products. If you want to make a product of these material, that's a totally different LCA. Okay, so there was a study, that was a paper that is published. Whatever I'm going to cover in this lecture are taken from this particular reference. So cradle to gate. So what is cradle to gate? What does cradle to gate mean? Raw material to product. So here what is a product? The product is just a resin, not the product you make with resin. Okay, so as per this particular case, cradle to gate means raw material to the plastic resin. That's where you stop. You don't look at what happens to the resin, what is made of the resin. That's a totally different. Okay, and here in this particular paper, about 9 different plastic resins and 4 different polyurethane polymers are actually subjected to LCA analysis. This is done by a private firm, Franklin Associates. It's an LCA company. And this was submitted, this report was submitted to the plastic division of American Chemical Council. Okay, it's called ACC. Okay, so ACC hired Franklin Associates to actually make LCA analysis for 9 popular plastic resins, just only resins. Okay, now let's say if I want to talk about PET, okay, polyethylene terephthalate. We'll take this as one example. Other resins include HDPE, LDPE, LLPD, LLDPE, polystyrene, polypropylene, polyurethanes, etc. Okay, so now the most important information that we need is the flow sheeting. Okay, if you're a chemical engineer, you know what's a flow sheet is. So you need raw materials to convert them into a product. Everything that goes into this process is put into a kind of a diagram, network diagram that shows relationship between various materials processes. So, so here we are talking about polyethylene terephthalate. Okay, I don't know if you're able to see from there. So what we have here is there are 2 important things that we need. One is this crude oil, and the other one is a natural gas. Okay, these are the 2 important raw materials. So from crude oil, what do? We basically do distillation, refining, right, cracking, and then with that what we do is we create ethylene. Okay, and then also mixed xylenes. So, xylene, as you know, is basically a molecule like this. This is xylene, okay, and ethylene basically has this kind of, it's a double bond, CH2 double bond CH2. So, ethylene and xylene, they do not exist by itself, so they have to be converted from crude oil, okay, and natural gas is basically methane, and from methane also you can produce variety of things. We can make methanol, acetic acid, and carbon monoxide, as well as ethylene. So, all these chemicals are made from natural gas. So, here the way it goes is, so from crude oil you make ethylene, from ethylene you make what is called ethylene oxide. So, ethylene oxide goes something like this, CH2, CH2O, this is ethylene oxide, okay. You remove one of the double bonds and then you put a oxygen between these two. So, that is called ethylene oxide. From ethylene oxide you get what is called ethylene glycol, okay. So, ethylene glycol goes like this, CH2, CH2, there is a OH here and there is a OH here. Crude oil, ethylene, ethylene oxide, ethylene glycol, okay. So, this is one of the important raw material for the PET production. The other raw material is the TPA, that is terephthalic acid. So, terephthalic acid formula is, you have this benzene ring and then you have COOH, okay, and this terephthalic acid is produced from xylene. So, from crude oil to xylene, and from xylene they separate paraxylene, which is basically this, and then this is converted into, this group is converted into COH group, this is converted into COH group, then you get terephthalic acid. So, now we got two important raw material, terephthalic acid, which is basically diacid, and then we have an ethylene glycol, which is a diol, okay. So, then the reaction goes something like this, you have terephthalic acid, and then you combine this with CH2OH, CH2OH, right. So, then what you do is basically you have a condensation of water here, right. Then basically from here you will produce so that is your polyethylene terephthalate, okay. So, it is basically an ester. So, when you have alcohol and acid condensing, you get an ester. So, you can see that this is the polyethylene terephthalate polymer, okay. So, coming back to this flow sheet, so we make ethylene, ethylene oxide, ethylene glycol, and then xylene, xylene to TPA, and so here you can see that we basically combine the terephthalic acid and the ethylene glycol and then make polyethylene terephthalate, okay. So, when you try to do LCA, this is the first information that we need. What are the things that you need to get into the final product, okay. Natural material or natural capital that we are using here are the natural gas and petroleum, which are taken from the earth, okay, and then from there you basically refine the products one by one, and you go through this intermediates, ethylene, ethylene oxide, ethylene glycol, xylene to terephthalic acid, and then you do this polymerization reaction, right. So, now once we know this, you can see that there are other things, there is this oxygen is used for creating this ethylene oxide, and there is also recycling of methanol as a byproduct. So, everything is included here, okay. So, once we have this, then we make assumptions. The LCA has to be done based on a particular assumption. So, here the calculation is made for every 1000 kilogram of plastic resin, in this case PET resins. As I said, the raw material, the natural capital that we use in this particular case are the crude oil and natural gas, and here the transportation is also very important, because all these materials are not available in one place. You are procuring different material from different place, so the transportation is also very important. And here fuel consumption is important for the transportation costs. Whereas in the case of a production process, they use off gas fuel, which basically means that in this process itself some gases will come out, and that can be used for other heating purposes, okay, some sort of a process optimization. And then LCA is conducted based on this ISO standard, ISO 14040, and the database is based on United States LCA database mentioned. And in this particular case, this database consists of data obtained from various resin making plants in United States, Mexico and Canada. So you clearly see that this is particular to the Western American countries, and to some extent Mexico also. Here the approach is only cradle to gate, not cradle to grave. So that means this is only up to the making of the resin, not anything further. So end of life options such as conversion of plastic products or product use, transportation to retail outlets, these are not considered. Okay, so so the analysis is only up to the resin making. Water consumption is also not calculated, because due to the lack of corresponding data for the raw material and intermediate chemicals. So you can see the limitation of this analysis. Whatever we are going to learn from this analysis, water use is not going to be considered. So that means if you are going to use this LCA data in a place where water is important, water is scarce, then you have to be very careful how you want to use this data. This is probably applicable where water is abundantly available, so you don't have to really factor in that. Also, the land use, erosion were also not considered due to lack of data source. So you can clearly see that the scope of the LCA, to what extent we can cover different aspects, depends on how much data we have, how much quality data we have. Okay, so clearly you can see that some things are left out because there were no proper data available, like water usage, land usage, environmental erosion constraints. So once you set up all these assumptions, then what they have done is, there is a so when you see this paper, you will see they have given a very broad analysis of what it takes. For example, the most important thing is this energy requirement. How much energy is going to be involved? So here the energy involvement is actually categorized into three parts. There is energy required to run the process. Okay, that means heating, cooling, and various process. If you are conducting a polymer reaction, you have to supply heat. Okay, there is going to be a heat involvement, energy involvement in the process itself. So that is taking about 33.3 gigajoules. Okay, 1 gigajoules basically means 10 power 9 joules. Okay, for every 1000 kilogram of PET resin manufactured. The second is in transportation. As I said, transportation also require energy in terms of fuel, diesel or petroleum or gasoline, and that also cost about 1.57 gigajoules. And then there is also energy of material sources. So what this means is, to make PET resin you need raw material, and the raw materials are natural gas and crude oil, but they themselves have to be mined. Okay, they are not available on the surface of earth, so they have to be mined, they have to be extracted from earth. So there is going to be energy involved in the procurement of those raw material itself, right? So that's what this energy of material resources mean. This is even before you do the process. Okay, this is like getting the raw material to the plant. That also costs energy, because these raw material have to be mined, they have to be extracted. Okay, so you can see the total energy is about 70.4 gigajoules. In this, almost 50% is for the raw material mining and extraction, and the remaining 50% roughly is about process. Transportation seems to be only up to 2%. Okay, so this data is now converted into percentage. That's all. So what we understand from here, we say that if you want to make 1000 kilogram of PET resin, the amount of energy that needed is about 70.4 gigajoules, right? Now, if you ask where are these energies obtained, okay, so the energy sources can be of various nature. You can actually probably burn natural gas itself to produce energy, or you could actually use petroleum coal is also used to generate electricity and various hydropower, nuclear, wood and other. So, this particular analysis is based on the PET plants in US, America, US, Canada and Mexico, and then looking at how these plants are procuring energy and what are the sources of this energy. This table is made. Okay. Clearly, you can see that a larger fraction of energy is met by natural gas and petroleum, okay, of the total, total energy cost. And there you can see that the amount of renewable energy like wood is there is no wood based energy. There is something called other. I think this probably includes non-conventional energy sources, maybe like solar, wind or something like that. And clearly coal is also playing a big role. Okay, in terms of percentage, you can see natural gas and petroleum are the largest energy sources for these processes, right? So, so we have dealt with energy requirement for PET resin. The next thing is waste generated. Remember, this waste is not about the waste generated because of the resin itself, but it is because to make the resin you are actually using material and some material is going to be wasted. Okay, it is about not the plastic waste, it is about the waste created to manufacture the resin. Okay, so here it seems that the landfilled waste, solid waste, this is also per 1000 kilogram of PET. You see about 33 kilogram of, for every 1000 kilogram, 33 kilogram of solid waste is landfilled. Some amount about 1 kg is incinerated, and sorry, I think there is a little bit of, yeah. So this is fuel, this is waste to energy. There is some misalignment here. Yeah. Okay. Okay. So I think the solid waste generated to meet the fuel requirement also is quite high. You can see that very large fraction is that, and this also goes same way. It also means that the waste to energy is 0. That basically means that pretty much no waste is converted into energy. So they are either landfilled or incinerated. Okay, so those are the two options. Okay, so solid waste generated, energy consumed. Now comes the emissions. So when you think about emissions, you can probably look at the last column. Okay, so everything is given in terms of total CO2 equivalent. I believe this is in kilograms. Everything is in kilogram. So if you see that the various gases that are involved, carbon dioxide, methane, nitrous oxide, methyl bromide, methyl chloride, but these are all all these things are much lesser quantities, whereas the dominant ones are the first three, largely CO2, next is methane, and then nitrous oxide, and then they sum up and then give a total amount of CO2 equivalent emissions, okay, for the greenhouse. So different process will have a different components. Okay, so in this case we are talking about only for PET. If you do this for some other resins, you will have a similar set of chemicals under emissions. Again, these are all based on the database of known manufacturers. So as I said, in terms of sensitivity analysis, what they say is that clearly it is a cradle to gate, not for a cradle to grave. So the comparison, if at all you make, is only with respect to the resin making, not about the end of life scenario. And if you look at this fuel production and energy values, these are all based on the data available as on 2009. The report came in 2011, but the data used was based on 2009. Usually one would average over 3 to 5 years, because these product prices can also fluctuate a little bit. The oil prices, the electricity prices can fluctuate a little bit. So a general practice is to average over 3 to 5 years, but this one only talks about the prices available as on 2009. Okay, so that's one of the limitations. So as I said before, it does not consider various other processes like eutrophication, acidification and other chemical pollutions, okay, because such data is not available in this database. Okay, so we have to be careful to use this data under these limitations, right. So now this is a kind of a comparison. So, we have looked at PET, okay, and the same analysis this report also gives for few other resins also. So, we are comparing, let us say, between PET, GPPS means general purpose polystyrene, okay. So, this is basically polystyrene. And this is high density. So, if you look at if you look at this, you have a PET general purpose polystyrene, and this is high density polyethylene. Okay, I think I can write here, yeah, high density polyethylene, and this is polypropylene, right. So, here so this so just like how I showed for PET details of energy, solid waste and emissions, same thing is done for other three, and we are comparing here. Here we are comparing based on 1 kilogram of each resin. So, you see that specific gravity basically means the density, which is specific to each polymer. This is more like the reason why we specify specific gravity is because sometimes we may want to ask the quantity not per kg, but per meter cube, in a volume basis also. If you need that, then using specific gravity you can convert this all in terms of per unit volume of the resins. Okay, so you can see the energy consumed are given. So, basically if I go back to this table, I mentioned that for 1000 kg you have 70.4 kilojoules, sorry, gigajoules. For 1 kg this will be 0.074704. That is what you see here, right. And similarly, if you look at carbon footprint, we showed this is for 1000 kilogram. For 1 kilogram it is going to be 2.733 kg, that is what this is. And solid waste generated, this is 141 kg per 1000 kg. So, for per kg it can be 0.141, that is this, okay. So, from that master data you can combine the total energy consumed, carbon footprint and solid waste. So, what we see here, we see that if you look at energy consumed, we see that the energy consumed are not very different from each other, okay. They are all about roughly about 0.07. Polystyrene requires a little bit higher energy, okay. From energy point of view they are all very similar. And if you look at carbon footprint, how much CO2 is emitted, equivalent CO2 is emitted, you see that the polystyrene ranks the highest in this table. Polypropylene and HDPE are very similar, and PET is something in between. And then how much solid waste is generated? If you see, I think the highest waste is created in PET. Again, it is not because of the PET products, it is just the PET resin making itself. PET resin making itself creates a lot of waste. In that, among these four, PET seems to form the highest amount of waste, okay, compared to polystyrene or HDPE. I think the between polypropylene and HDPE, I think the values are very similar, okay. But among this, what you can say is that polypropylene and HDPE seem to rank best in this particular case, because they seem to have low carbon emission, they seem to have the low solid waste generated compared to PET and PS. What it means is, if you want to make a product, okay, and if you want to, if you want to make a product and you are looking at which resin is more viable, given these options, you could probably choose polypropylene resin or HDPE resins, okay. So, the LCA analysis comes handy only at this point of able to compare between different resins which are polluting more, which are costing more solid waste, and which are expensive to create, okay. Apparently, here energy requirements are very similar, so that is normalized. Whereas, if you look at carbon footprint and the solid waste generated, we are a little bit siding towards polypropylene and HDPE compared to PET and polystyrene, right. Any questions at this point? Okay, so these are all based on conventional petroleum based fossil fuel resins. Okay, I also have some discussion on PLA. So PLA is a polylactic acid, that is one of the bioplastic that is commonly used in the market. If you go to Sangeeta, or if you go to many of the eating outlets, if you carry on anything, you will see that most of the bio bags that you have are based on PLA with some mixed with some starch and various other things. And the data I am going to present are based on this paper. Okay, the eco profile for current. So the INGEO is a trademark name for PLA resin produced by NatureWorks, which is a US based company that produces PLA, right. So here again we start with the flow sheet. Okay, so in the case of PLA, it is based on corn. Okay, so you produce corn, you harvest corn, dry it and transport it to the corn wet mill. In there you use corn and then make what is called dextrose. Okay, dextrose is also a sugar, and from dextrose you convert them into lactic acid, and from lactic acid you produce lactide, and from there you produce polylactic acid as a resin. So if you look at here, if you consider the first process, corn manufacturing, it is an agricultural process. Okay, just like how we grow rice and sugar cane, corn can also be produced. What do you need for that? You need electricity, fertilizer, natural gas, diesel, gasoline, propane, all that related to production, harvesting, transport. You also need other things like, for example, carbon dioxide, irrigation of water, herbicides, insecticides, seed corn, limestone. So that means in the agriculture process of creating corn production, everything that goes in is actually accounted in this particular analysis. As much information as you know, you can put it up there. Okay, so that means you have to really know what it takes to produce corn. Okay, you have to think like a farmer and look at throughout the cycle from the initial to the final, what goes in, what are the things that you add, what are the resources you add, what are the materials that are used, that has to go. Okay, once we get this corn wet meal, and then there you have this dextrose production. In this entire thing, you again use natural gas for energy, steam is also used, electricity, water, sometimes compressed air and nitrogen. And then this is a biochemical process, from corn to sugar to polylactic acid. It's actually an enzymatic biochemical process. So you're going to use a lot of substrates, enzymes, salts, acids, nutrients, various things goes in. So my point is that this entire thing is system boundary. What comes in is a raw material from earth, soil, water, carbon dioxide, fossil resources. That means you're going to feed some fertilizers, you're going to put some manure and all that. Okay, so that was goes in. What comes out? You get polylactic acid resin, and along with it you have emissions, water pollutions, solid waste generated. So the idea is to account for all this information. Okay, so given that these are the raw material, given that these are the processes that are involved, how much is the emissions, energy required, solid waste created, water generated. Okay, so in this particular paper they have looked at all these processes. Okay, assumptions, again as per the ISO standard 14040, assumptions have to be clearly mentioned. Okay, so that we know what are the limitations, applicability of these analysis. So here the basis is 1 kilogram of INGEO resins. So here also you can see it is based on cradle to gate. End of life options, conversion to plastic products, product use, transportation to retail outlets are not considered. So this is not about what are you going to do with your plastic resin. Okay, so later on I will talk about LCA of products. Okay, that is totally different part. So here we are talking about what it takes to make PLA resin. So here in this particular paper they have cited this Bousted 5.0 methodology and associated software for the database and for the analysis of LCA. All inventory and LCA calculations are based on as per the standard. Okay, so these are the assumptions. So if you see pretty much the assumptions for PET and assumption for PLA are pretty much the same. Both are considering cradle to gate approach. They are not considering any end of life options, right? So here you can see that, without going to the details, the paper, if the original paper, if you see, all the details are given. So here for every 1 kilogram of PLA, polylactic acid, the energy consumed is 0.064 gigajoules. Is it comparable to PET? How much was it for PET? 0.074. Okay, so very similar. The energy cost is not very different. Carbon footprint. How many kilogram of CO2? It's about 1.24 kilogram. How much was it for PET? 2.2. So that you can clearly see that the carbon footprint of making PET versus PLA is seem to have lesser impact. Solid waste generated 0.14, right? 0.14. So here is actually little higher, okay, almost twice. Okay. In the PET case, we didn't account for water consumed because that data was not available. But in this PLA analysis, the water consumed is given. You can see for 1 kilogram of PLA resin, you need about 50 kilogram of water, 50 liters of water. Okay, so that's a lot of water. Water consumption is important. Okay, because it's related to agriculture. To grow corn, you need water. So you can see the impact of water utility. If you have a nation with a water scarcity, producing PLA there cannot be viable. Okay, so water consumption becomes very crucial. So eutrophication also reported because this data was available, but we can't compare this with PET resin because the data is not available. So idea is that when you do LCA, you can try to generate as much data as possible based on the database available. Okay, so that is this. And now I want to ask you to do an activity. This paper is available online to download. Okay, I have shown some data for PET. It also shows data for LDPE, LLDPE. That means this is low density polyethylene. This is low linear low density polyethylene. And polyurethane, they have two, flexible form and rigid form, and PVC also they have. So my request for you to is to download this paper and then make a comparative statement and find out for each of this per kilogram of, I think they have reported for per kilogram or per 1000 kilogram, you can see, find out the density, energy consumed, carbon footprint, solid. These are minimal data. They may show other data also for others, okay, but at least for these 4 different resins, try to complete this table and suggest among these which one would you prefer.